All right, on this first example here, we are going to be looking at a pendulum. And it says we have a child on a tire swing that is suspended from a 6-meter rope. How long does it take the child to make one complete swing? So they're going to go, back and forth. So when we are looking at how long does it take to make one complete swing, what we're looking for is the period. And our formula for a swinging pendulum and a period is we have the period is equal to 2 pi times the square root of the length of the pendulum divided by whatever the gravity happens to be on whatever planet you're on, I guess. Okay, so we are looking for t. 2 pi, that is a constant. Now the length of our pendulum is 6 meters, and it does need to be in meters to work out with our acceleration due to gravity. Now, for gravity, you can either use 9.8 or 10. Doesn't particularly matter. I'm going to go with 9.8. And our unit for gravity is meters per second squared. Now, we can see that our meters label is going to cancel out here. And I'm going to go ahead and divide the 6 and the 9.8. And then I'm going to rewrite my formula here. So we would still have 2 pi and then the square root of 0.61. I'm not going to write out the whole thing. And then our label is going to be seconds squared. Now, the seconds looks like it's in the denominator, but because it's a complex fraction actually where we have a fraction here and a fraction here, when we invert and multiply, that actually brings the second squareds up to the numerator, which is why I put it right up here on top. Now, at this point, the labels, when I square root this number, I have to also square root the unit. So the square in the square root on the label will allow my units to turn in just to seconds. So I'm going to go ahead and take the square root of the numeric portion of it. Let's see. And that ends up giving me 2 pi times 0.782, etc. And that is still going to be in seconds. Then I can go ahead and just multiply by 2 pi. So there we go. And I get the period to be 4.916 seconds. Oh, that should be a C. Jeepers criminy. Let me erase it. That was terrible. S-E-C. And now when I check sig figs, it looks like I only get one significant figure, so I would write that down as 5 seconds would be my period. Now on part B here, it says, let's say the pendulum has a period of 6 seconds. How long would the pendulum be? So in this one, we're still going to be using the same formula here. T equals 2 pi times the square root of L over G. I guess it's right there. But we have to put our values in different locations. So this time the period is 6 seconds, so that's going to go in the location for T. So I'm going to end up with 6 is equal to 2 pi times the square root. Now L is what I'm looking for, how long? And then I still have my 9.8 meters per second squared for gravity. So now because my variable that I'm looking for is not isolated, it's mixed in with all this stuff, I have to use inverse operations in order to solve for it. So the first thing I'm going to do is I'm going to get rid of this 2 pi. And since the 2 pi is being multiplied by that quantity, I need to divide both sides by 2 pi. And that will get rid of them on the right-hand side of the equation. And then when I take 6 divided by 2 pi, that turns out to be approximately 0.95. Now, I'm not going to write out the full decimals, but just know that on my calculator, I am not clearing the number. I'm just going to be doing this as a running value, and that will help eliminate rounding errors. So at this point, I have 0.95 with a whole bunch of other decimals is equal to the square root of L over 9.8. Next thing I have to get rid of is that square root. So to undo the square root, my inverse would be to square both sides. Okay, so the square and the square root will cancel each other out. And when I square the answer that I had on my calculator for that 0.95 value, that turns out to be 0.91, and again with a whole bunch of decimals. And then on the right-hand side, I'm only left with L divided by 9.8. So the last thing I have to get rid of is dividing by this 9.8. The inverse of that is multiply by 9.8, so I need to do that to both sides. On the right-hand side, those will cancel out. And on the left-hand side, I get 8.9365 with more decimals is equal to L. Now I need to go back and check how many significant figures I get. It looks like I only get one, so I would round that to 9 meters is the length of my pendulum. Okay, now one of the next questions was, what's the difference between bow waves and the Doppler effect? So essentially a bow wave, it's the name given to a type of wave produced, and it's based off of the V that comes here or here. And that happens when an object is moving faster than the speed of the wave itself. So a bow wave is strictly based off of the shape that is produced by the successive waves. Now, the Doppler effect, I know the textbook gives different examples of like your typical siren, if a police car or a fire truck or something like that goes past you, there's sound you can hear. But what it is it's the changing in the frequency due to either the motion of the source, so the fire truck moving, or it can also be the motion of the receiver. So what I wanted you to do is try to visualize that you are in a wave pool. So if you've ever been to a wave pool, essentially they have a mechanism down here that generates waves at constant intervals. So we would have the frequency of these waves being generated from the source is consistent. Now let's say that you are, standing right here. And if you were to just stay stationary, these waves would crash into you at a constant frequency. Let's say there's one every 3 seconds hitting your legs. Now, let's say a wave hits you and you start to run forward. Yes, I know running in water is hard, but let's pretend it's not. And you start to run forward. Well, now you're going to run into this next wave because this next wave is still moving towards you also. Instead of it taking, I think I said 3 seconds, instead of it taking 3 seconds for the next wave to hit you, because you are running towards it, it's going to hit you, let's say, in 2 seconds. Okay, well, and as you keep running, what happens is these waves will start to hit you with a more rapid frequency. So it's a change in that frequency that the waves are hitting you because of, in this case, your motion. Now, it can also be in the other direction. Okay, so let's say, again, you're standing here, that wave hits you, and then you start to run away. Well, this next wave is essentially chasing you, so it's going to take longer than 3 seconds for that next wave to hit you. Okay, so again, though, we have a change in frequency, and it's due to the motion of the source or the receiver. Now, if we look at these bow waves up here, I'm going to look at example B because it's the easiest one to try to draw on. You'll notice, let's say that you were standing, let's say you're standing right here. These waves are going to hit you with the same frequency. And part of the reason that we can tell is because notice that the distance between them, between each wave, is consistent. So the frequency with which those waves hit you is still going to be the same. So there is not a change in frequency in a bow wave. Okay, the bow wave is kind of describing the shape produced when we have those differences in speeds of the objects in the waves, versus the Doppler effect produces a change in frequency because of the motion of either the source or because of the receiver.